Thank you, Muntasir, and good morning, everyone. This morning, I'll be presenting to you an experimental research on seismic retrofit and quick repair technique involving transverse prestressing of reinforced concrete bridge columns. As you all know, reinforced concrete bridge columns are vulnerable to seismic excitations if they were not designed following current code requirements. And they can be potentially vulnerable against three design deficiencies. The first one is not having sufficient transverse reinforcement, hence shear strength. And second one is lack of concrete confinement, once again, not having sufficiently designed and detailed transverse reinforcement. And some of the older bridges also have improper splice length, especially in potential plastic hinge regions. And any one of these deficiencies result in significant column damage. And I don't need to go through many examples, but we all know that especially short columns can develop transverse diagonal tension cracks caused by shear, and not having sufficient transverse reinforcement results in shear distress. And there are many examples of lack of concrete confinement. The one on the left side you see is lack of concrete confinement. These are continuous reinforcement in transverse direction, subjected to significant axial compression. The one on the right-hand side is taken from Northbridge earthquake, where there was a significant lateral deformation reversals. And we can also find some examples of lack of splice deficiency in columns. So what I will be presenting to you is called retrobelt seismic retrofit and quick repair technique. It's a system of external prestressing, basically applying transverse compression on concrete in order to, number one, not allow transverse expansion, and this would occur, of course, if you have shear deficient columns, and there's a tendency to develop diagonal tension cracks, or if there's not enough confinement reinforcement. Of course, for columns to fail it, they have to expand laterally. Once again, lateral prestressing would eliminate or reduce this tendency of lateral expansion. And it does also provide lateral clamping forces to improve bond in these splice deficient regions. So the technique is fairly easy to apply, and all you need is prestressing strands, and in our experiments we use 7-wire strands having 15 millimeter nominal diameter, and then there are special anchors which tend to connect the two ends of individual hoops, and then a hand-held jack to apply prestressing. Here you see on the right-hand side a circular prestressing, and then on the left-hand side application to square and rectangular columns, which I will expand more little later on. So the sequence of application involves cutting the strands to appropriate length, and then inserting them through the anchors, and anchors have prestressing wedges at the ends, and then you have to apply prestressing by means of a hydraulic jack, and then you lock them, thereby prestressing the columns in the transverse direction. Here's an application for square and rectangular columns, which does create challenges. In circular columns, obviously, hook tension would provide uniform lateral pressure. But when we have square or rectangular columns, then we need to complete their geometry to either semicircular or elliptical shapes by means of, in this case, using steel HSS sections as razor units, and then welded to it are half pulleys, as you can see, and this does increase possibility of developing uniform stress. And you can see on the right hand side the top view, even though it's not a perfect circle, it does apply close to uniform lateral pressure. The first test that I will show you is a shear deficient square column, and this column has 550 millimeters square cross section, 10M ties, which is we're having 11.3 millimeter diameter. We're spaced at 300 millimeter spacing. This certainly does not conform to current codes of practice, and hence it did fail at about 1% drift. This is a 1.5 meter tall column representing shear span, basically half the length of actual column with fixed ends. As you can see, this was shear dominant, and you could see diagonal cracks forming on the right-hand side. But once we applied transverse prestressing, in this case, we went up to 25% of ultimate capacity of 7-wire strands, which was 1860 MPa strength wires, with a spacing of 150 millimeters. So the original column had 300 millimeter ties. This time we added 150 millimeters external prestressing strands. The hysteretic response improved quite drastically, and there was virtually no strength decay up to 4% drift, and there was a gradual strength decay starting at 5% drift. So this is a significant improvement in shear resistance. Here are the details of the razor discs and how the prestressing force was distributed around the perimeter of the exterior perimeter of the column. Another test result is this time on a circular column. Once again, shear dominant circular column. You can see the damage state at 2% drift on the right-hand side. This column had 610 millimeter circular cross section. Once again, internal ties were spaced at 300 millimeters, having 10M bars. And similar to the previously tested square columns, they started developing diagonal tension cracks, which started increasing at 1% drift, and we cycled at 1% 3 times. As we pushed the column towards 2%, it basically started unloading and suffering shear failure. Another example of insufficient column design was lack of concrete confinement. This time we tested a 2-meter long column, so that is typical of a 4-meter column, fixed ends, because this was up to the point of application of the load, so it's representing shear span. So these were flexure dominant columns. First, we're looking at a square column having 500 millimeter cross section with same type of internal ties having 300 millimeter spacing. And this time, because it's flexure dominant response, we were able to complete cycles at 2% drift, and it started decaying at 3% drift. And when we applied transverse prestressing, once again at 25% of ultimate capacity, and I will discuss the significance of initial prestressing when I talk about the design procedure. we were able to develop 4% drift without any problem. Once again, strength decay started taking place at 5% drift cycles. Another example, this time flexure dominant circular column, having 508 millimeter circular cross section, similar detailing of ties, and similar response as the one we just discussed for square columns, basically completing 2% drift cycles, but suffering damage at 3% drift. But upon transverse prestressing, we went up to 4%, similarly improved behavior. Another set of columns that I'd like to show you are the ones that had splice deficiency. Here we had 300 millimeter splice length. This is not acceptable by current standards, whereas it was permitted prior to 1970s and even 80s. And here you can see at 1% lateral drift, the bars started slipping. You can see significant pinching of hysteresis loops and strength decay almost by 50% upon forcing it to deform to 2% drift. And companion column was retrofitted, as you can see in the splice region, and this provided clamping force, and we were able to get 4% drift without much decay. And I'd like to discuss design procedure for these columns. First of all, for confinement design, we had developed earlier a design expression for confinement of columns as a function of drift ratio. This delta shows the drift you wish to attain. You may want to go up to 4% drift if it is in a seismically active region, but 2.5% drift if it's moderate seismicity. So transverse reinforcement ratio, this is area of transverse steel divided by BH, concrete area, could be obtained with this expression with certain limitations to cover to a core area ratio, not to be less than 0.3, and axial load ratio at least 20% of P naught. And these are the limitations within which the expression was calibrated against test data. So for external prestressing, we could use the same expression, but K sub C is the effectiveness, confinement effectiveness parameter. It's equal to 1 if you have the best confinement arrangement, which is circular reinforcement with uniform hoop tension. In this case, because we're providing almost perfect confinement either on circular columns by direct application or square and rectangular columns through those razor blocks, Kc can be taken as 1. And this time there is no cover to talk about because it's externally prestressing. That's why we substitute the minimum cover to core area ratio in this expression. And then we end up getting this expression for area of prestressing strands. So this is a function of drift. And the one significant point to note here is the transverse steel strength that appeared in this expression. And this is replaced by prestressing steel, which consists of initial prestressing. In our test, we applied 25% of ultimate. And then this would induce active lateral pressure, but then it also has capacity to confine in the passive pressure range as the active pressure is neutralized, then the column has ability to expand laterally. And in our experiments, we recorded 0.3 to 0.5% transverse strain before the column started decaying. And hence, in our design expression, we allowed 0.3% transverse straining. So that is to be added on to this active pressure range. And the spacing is limited to h/4 or 150 millimeters, whichever is smaller. For the splice deficiency, we use the same expression for determining required area of prestressing. However, experimentally, we observed that slippage takes place at 0.1 to 0.2% transverse strain, and hence we limit prestressing stress to whatever initial stress is applied, plus only 0.1% of concrete expansion before the bars start losing their bond and start slipping. So it's the same expression with tighter limitation for lateral expansion, can be used for splice deficiency design. Shear design can be similar to VC plus VS approach in reinforced concrete, but this time we have V prestressing, the shear resisted by prestressing force, and prestressing force would then be equal to, once again, the stress in prestressing. And here we're assuming that V sub C is active up to 0.2% of transverse strain. This is consistent with grade 400 MPa steel or 60 KSI steel. And of course, when you go beyond that, then diagonal tension crack capacity or aggregate interlock may not continue resisting V sub C. So we've taken that as a limit. Other than that, we've simply added VES, which provides active prestressing as well as additional shear reinforcement. I'd like to say a few words on use of the same technique for repairing columns. Here we're looking at a repaired column. Maybe I should...
Sorry to interrupt, Dr. Saatcioglu. You have 3 minutes.
Okay. Well, here we are looking at a column that was damaged due to shear. This is a rectangular column, once again, failing at 1% drift. But when we repaired it, we stopped the test at 1% when we realized that column was about to fail, and we repaired it. As you can see, we recovered quite a bit of strength, but we did get asymmetry in hysteretic behavior. This was to be expected because column had already slipped in one direction over this diagonal crack. So strength was maintained, deformation was controlled, but in one direction, it was able to deform more. So this is an example of application for a quick repair technique. And this technique was recognized by Caltrans a number of years ago, because often after the earthquake, there's not much time to close bridges to traffic and go through lengthy repair process. Whereas if cracks did not open up too much, all you have to do is bring these strands and wrap them around and pre-stress them and open the traffic to service. One has to talk about protection against corrosion of the steel because it is placed externally, and we tried different ways of protecting steel, including using sacrificial devices to prevent corrosion. But no matter what you do, there's a statics problem. You certainly don't want to expose these retro belts, and one could use maybe column covers, or in this case, we tried shotcrete, and we were able to go up to 5% lateral drift without shotcrete detaching from the column. So this is one way to protect against corrosion. A typical field application would involve only closure of one lane, and then a single elevator type crane with 2 labor would be sufficient to apply this prestressing. So this is in terms of construction time as compared to steel jacketing, for example. It is much quicker and much cheaper as steel cost goes by weight, of course. So here's an example of how it can be applied in practice. I'd like to conclude my presentation by reiterating that the retrobelt system of transverse prestressing can be used to control diagonal tension cracks due to shear, and it also induces additional confinement pressure while providing clamping forces in the splice deficient regions, and the application can be quite cost competitive. Thank you for your attention. If there are any questions, I'd be happy to answer them.
So thank you, Dr. Saatcioglu, for your nice presentation.